So my lecture is devoted to the topological approach in crystal structures and how this approach can help the simulation methods, the quantum mechanics methods, and other mathematical modeling methods. First, let's ask ourselves, why do we need topological crystal chemistry? We know two branches of solid-state science that describe crystal structures. This is crystallography and crystal chemistry. Crystallography deals mainly with atomic positions. It does not consider chemical bonds. It considers the crystal structure as separate atoms, as points. Crystal chemistry works with chemical bonds, with some kind of edges between nodes or between points. Crystallography considers atoms arranged in periodic lattices. Again, there are no connectivity between atoms in this case. Crystal chemistry arranges bonds into nets. Also periodic nets, but these nets are connected. And finally, crystallography considers geometrical properties, mainly geometrical properties of crystal structures, while crystal chemistry deals with topological properties. So crystal chemistry is essentially, naturally, topological science. Of course, these two branches are interrelated and they can exchange the knowledge. And of course, crystal chemistry uses mathematical background of crystallography, but also crystallography can get some information from topology concerning the relations between crystal structures. Now, we need not only topological crystal chemistry, we need computer topological crystal chemistry. Why? Why do we need computers? Let's look at this girl. She wants to analyze this rather weird crystal structure. And she's doing it with some standard method. She's looking at the images of this structure and tries to understand what is it. And of course, as a result, she will get some description, but it will be essentially subjective. Because if we take some other girl, she will consider the same structure from another point of view. And she will describe it in some other way, and she will be sure that this way is the best one. Both girls will consider the structures the same structure from different point of view, and they will be sure that they have the best view of this structure. But we need to replace this picture with some numerical information computed by some strict algorithms, and this means that we will describe this crystal structure in the same way in different computers by different people, so we will get some objective information about the structure. This is the first reason why do we need computers. The other reason is that now we have a really huge amount of crystallographic information in worldwide crystallographic databases. Totally more than 700,000 entries in the databases, and of course to find any rather general regularity in this amount of information, we need computers. Now, let's consider how topological methods can help simulation methods. Quantum mechanics or other simulation and mathematical modeling methods provide us with quantitative evaluation, but for a single compound. Crystal chemistry, considering topological and geometrical properties of crystal structures, works very fast. And it can obtain only qualitative or semi-quantitative evaluation of the properties of crystal structures, but can do it for large groups of compounds. And in this way, we can find really general regularities in electronic databases. So we could probably merge these two branches to get some hybrid method that can keep the advantages of each branch. But how to do this? One of possible solutions of the topological problems in crystal chemistry is the TOPOS program package. We developed this package during almost 25 years, and it is available for free in internet. Generally, the topological analysis in TOPOS can be reflected by this scheme. We start from initial crystal data. We can use, for example, C files. Then TOPOS automatically restores the topological information about the crystal structure using the program AutoCN. And as a result, we obtain atomic net, periodic atomic net. Then TOPOS analyzes this net and automatically recognizes structural groups. Moreover, if there are several different representations of this structure, for example, you can select clusters, or you can select polynuclear complex groups, or for example, you can consider this structure as an ordinal coordination compound, etc., etc. TOPOS provides you all possible variants of the structure representation. Then the structure is simplified by replacing the structural groups with their centers of gravity. And with this simplified net, TOPOS can analyze a lot of different topological properties like entanglement, stylings, dual nets, and classify all these objects using standard scheme. Also, there can be used some other methods like Voronoi polyhedra method, analyzing atomic packings, and we can provide hierarchical comparative analysis of different structures. Now let's briefly consider how the overall topology, I mean the topology of the whole structure, is described in TOPOS. We use this pioneer method that was described long ago. The problem is that we have infinite structure, and we have infinite set of bones, infinite system of bones. And we should work in some way with this system in computer, but we need to make it finite to work with it with computer. How to do this? The methods means that we keep only the part of structure inside the unit cell, and we break the bones passing outside the unit cell, and then we close the broken bones passing through opposite faces of the unit cell together. As a result, we obtain some loops, some multiple edges between atoms, but this information, the information presented here, completely describes the total topology of the whole structure. And this object, this object is called labeled quotient graph. It is finite, and it can be used in computers to describe the topology, up to isomorphism. Now, how to distinguish all our overall topologies in TOPOS if we present them in, as a labeled quotient graph? We use several topological indices that are described in several papers, in a number of papers, and the most important are these four types of indices. Let's consider briefly what does it mean. For example, the coordination sequence means that we take some atom, any atom in the structure, and then we consider subsequently the coordination shells around it, the first one, the second one, etc. And we get the number of atoms in each coordination shell. Other topological indices, point symbol, extended point symbol, and vertex symbol, deal with rings, cycles, some closed paths in the structure. And this information, here these numbers show us the sizes of such cycles. Altogether, this data provide us with the description of this structure of this topology up to isomorphism. And using this information, TOPOS compares this data, this numerical data, with a large collection of topological types. And as a result, it assigns topological type to this structure. We can compute also other indices, and all these indices describe the topology strictly. Now, how can we generate overall topologies in TOPOS? Let's consider this rather complicated example. This is a structure that contains different kinds of atoms and different kinds of bonds also. Both valence bonds, hydrogen bonds, van der Waals bonds, etc. And we need to understand what is the topology of this structure. According to TOPOS, we need to assign different roles to all atoms of the structure. First, origin atom. This is the atom of the future simplified net. So these atoms will be kept in the simplified structure. Removed atoms are simply removed, should be simply removed from the structure together with bonds. Contracted atoms are the atoms that also should be removed, but the bonds in this case not disappear, but they are close to the atoms, so-called target atoms. As a result, the connectivity of the total structure is kept in this way, but the structure becomes simpler. For example, in this case, we can assign these roles to the atoms: origin atoms, all cations; removed atoms, all atoms belonging to the water molecules, so we ignore water molecules. Contracted atoms, phosphate oxygens, and target atoms, phosphorus atoms. This means that we consider phosphate groups as a whole. We approximate them as phosphorus atoms. As a result, we get this much simpler topology, and we can simplify it more by contracting these two coordinated atoms. And this is a final so-called underlying net that represents the overall topology of the whole structure. And this net can be automatically recognized by TOPOS. This is three-letter symbol, is one of the nomenclatures that used to designate the topological types. This is topological type TCS. Now one example. Why do we need really to know the overall topology for practice? Recently my German colleagues synthesized this new modification of antimonist square site. This is high temperature and high pressure modification. And they asked me to analyze the topology of this structure. With TOPOS I get the topology, this topology that is recognized as this topological type. Then I analyzed all structure types in inorganic crystal structure database, almost 6.5 thousand structure types, and I found only one example with the same topology in this array. This is the framework, this composition of framework in this compound. And in this case, this correspondence is not given by chance, because these structures, these frameworks, are really similar to each other, even chemically. Because if we consider antimony atom together with lone electron pair as this pair of atoms in silicon oxygen nitrogen framework, and also we match oxygen atom in antimonist square site and nitrogen atom in the framework here, we can get the total similarity between the chemical composition of these frameworks. What does it mean? We know that there are two other modifications of antimony square oxide, alpha and beta, and they have another topology. And we can ask ourselves now, can we synthesize this kind of network? Probably using some other cations, we can obtain other topologies for this framework. So you see that we can find some similarities between chemically quite different compounds. Nobody could find such similarity by hand. This is impossible. Now let's consider how overall topology matches local topology. We can describe, according to TOPOS, the local topology with the concept of coordination figure. Let's consider these three different chemical objects. Here we have just atoms as centers of structural groups. Here we have ligands, rather complicated organic ligands, and here we have clusters. But in all cases, all these objects give us the same overall topology. So topologically they are similar. They are chemically different, but topologically similar. This is the way how to find similarities between different chemical compounds, even quite different by nature. Now we can think what can be the relations between local and overall topologies. We can consider primary building units as coordination groups or coordination figures. We can now grow it more. And the question is, what is the minimal part of the structure that predetermines the topology, the overall topology? For example, is it enough to predetermine the overall topology of the structure? Indeed, in many cases, such secondary building units give us this layer. But not in all cases, and TOPOS will give you all possible variants with these secondary building units and with different topologies. And you can decide which topology is reasonable in this concrete case or it is not reasonable. We can summarize these relations and build the total scheme. We can start with atoms or some structural groups in general. We know, for example, that this atom can have coordination number 6. We know some typical coordination polyhedra or coordination figures for this atom. Then we can construct different coordination figures by replacing some coordination sites in these groups with terminal ligands. We get different figures from the same figure, for example, from octahedron. And then we know which secondary building unit can be built from these figures. And finally, we know which topologies can be obtained from these coordination figures. So if we have this sequence in total, we can predict in some way which structure can be obtained from a given from a given structural group. How TOPOS knows which groups can provide which topologies? For this purpose, we organize a special kind of topological collections in TOPOS. The most important at the moment is the so-called topological databases collection, TTD collection. It contains now more than 70,000 entries, 70,000 different topologies. And it includes also all other topological databases of the world. And with this collection, you can easily find a given topological type, for example, diamond in this case, and we can get a lot of information for this topology. For example, another type of topological collections in TOPOS is topological types observed collection. This collection shows us in which structures this topology occurs. Again, this collection grows very fast in the last years because we always process the last updates of crystallographic databases, and we get the information about topologies of complex groups in these structures. This collection is embedded into TTD collections. So, for example, for diamond, we can find in which structures diamond occurs. This is diamond, and this is a list of structures where this topology was found. One more topological collection is topological types relations collection, TTR collection. This collection shows us how different topological types interrelate. For example, we can take diamond again and find in TTR collection that diamond is related to this list of other topologies. The diamondoid topology can be transformed into this topology by some way. And TOPOS will show you how to transform this topology to other topologies. Now, with this list of 3 collections, we can answer these questions, really. We can obtain the net topology for a particular structure. Just open it in TOPOS, just go to Comment tab, and we get the information about overall topologies for this structure. Then we can get representatives for a given net topology. Again, for diamond, for example, we get more than 1,000 representatives, and these are reference codes in this case in Cambridge Structural Database. We can find the relations between different networks. Again, for diamond, for example, we can find a lot of relations. This is diamond topology, green net, and the black net is another topology, the topology of silicon atom and thorium silicide. We can transform one topology to another, considering the centers of dumbbells. In one case, we will get diamond topology, or we replace in diamond the nodes with dumbbells, and we get thorium silicide topology, etc., etc. We can also find which topologies are the most abundant, which are rare. For example, here we see that diamond is really one of champions by occurrence. And we can also find the topological descriptors. I told about this before. With these methods, we analyzed different compounds. First of all, metal-organic compounds, metal-organic frameworks, and we get the total statistics about occurrence of the nets. Again, you see here the diamondoid net is the first one by occurrence. So you can easily construct such distributions with TOPOS. And we did the same for 2 periodic coordination frameworks. We get the list of the most frequent 2 periodic coordination networks. And in this paper, we announced for the first time the idea of creation an expert system for crystal design using topological information. For this purpose, we describe the local topology with some special symbols. Let's consider some examples. These are the initial structure. This is a simplified structure, honeycomb topology. This is another kind of topology, again, initial structure and simplified one, etc., etc. And these structures contain some ligands that are coordinated by some way, and this way can be easily also write down into the databases. And then we can analyze this type of coordination. This is the method described in this paper. Now we can try to predict some, for example, two periodic motifs. Let's take as an example hydroxyacetate as a ligand and cobalt atoms. Sorry, there are some movements of signs here. Cobalt atom as a central atom, as a complexing atom. If we consider only these structural groups, we get this stoichiometric ratio, this composition of the structure. And for this, then we look into databases, topological databases of TOPOS, and we know from these databases that hydroxyacetate has mainly these two kinds of coordination. And for cobalt atoms, we know that in 7.8% it has the coordination number 4. And in most cases, it has coordination number 6. And as a result, we get this local topological information for these two possible local topologies. And again, from TOPOS, we know that this topology provide us with very high probability the same square lattice net. Here, even in all cases, you will get from these local fragments this kind of two periodic net. So the total, the overall probability is also very high, 0.91, 92. So we can create the expert system as a result in this general scheme. First, expert system asks you for some initial data. For example, which ligands do you use, which complexing atoms, which, for example, other structural groups like clusters, etc., etc. Then it runs inference machine, and this machine will use knowledge database that is based on the topological databases of different levels. I told about this. So we start from initial crystallographic data, and we get a lot of topological information that can be used to predict structures. And as a result, we get some expert conclusion. I will not talk in detail about other TOPOS collections. Now we are creating very intensively the collections of different local objects that can be found in real crystal structures. For example, a collection of polyhedral cages, metal nanoclusters, these kinds of objects. Then collection of polynuclear complex groups. For example, these kind of groups. Again, this is the initial group, and this is the simplified one. And we prepare other collection like these, like some structural groups, molecular ligands, etc., etc. And with all this information, we can predict in some way with some probability which overall topology we can obtain from the initial finite objects. We use TOPOS. I don't see the letter S at the end, but it is some incompatibility with Macintosh system, I think. So I am finishing. Now we come back to the initial question, how to merge these two approaches. And the possible question, in my opinion, is this one. We can make this question a bit more little, and probably we can use some combination of quantum mechanical packages like USPECH and topological packages like TOPOS. And we can solve with this combination very important questions, very important problems concerning the prediction of crystal structures. Thank you for your attention.